Hi, this is Shane Mueller, and this is a screencast of Chapter 8 of this textbook, Applied Statistical Analysis in R. You can get all the materials here at this website, and there'll be a link in the description. And today we're going to be talking about Chapter 8 of this book. The book is available through this link here, and I have it open in another window. So we're going to be talking about Chapter 8, Inferential Statistical Tests. Let me go back here, and you can get all the material let's see, if you follow this link, you're going to probably want to download this file, Chapter 8 walkthrough, and put it somewhere convenient. You can right click and save as. I have moved it to a whole folder called Chapter 8 where I can edit it and work on it. And you just want to make sure you can open this in RStudio. And let's see, I have R open. Let me navigate to where it is and open it and see. Okay, so today will be maybe a little lighter on simulation and testing than usual, because there's still some sort of practical theory to think about how these inferential statistics work. And the first thing to get to understand is what this the whole endeavor is about. And there's a lot of confusion. Even people who use statistics daily will sometimes think that the purpose of statistics are different than what it's doing mathematically. And in fact, researchers have done studies about what do you think t-test is doing, and given 7 options, and there's only one that's right, and very few people get the right one correct. So really, what you have to think about in all inferential statistical tests is that you are trying to make an inference about a population based on a sample. And that can be illustrated here. We've got some population of observations, people, cases, whatever, and you can only sample a few of these. Now, why could you only sample a few? It might be really expensive. It might be time consuming. It might not be feasible. Generally in like a presidential election, the newspapers that do polling and the politicians who do polling can't ask every person who's going to vote every week to see how they're going to vote, so they rely on sampling. And they couldn't even reach everyone even if they tried. Now, there's a lot of problems that you have with big data where you don't have a sampling issue. You may have access to all of the past data. Now, there still may be inference, but the inference is a little different in those cases. So, for example, let's say you're Facebook and you have millions and millions of records of how people respond to ads, and you want to know, well, is this advertising? You show some people an ad, and then later you find out if they converted or they went to the website and bought something. Well, in that case, you may want to know, well, does the proportion of people who went to the website and bought something greater for the people who saw the ad versus didn't see the ad? And so the question is, well, what is you really may have all the data, and so the inferential problem or the inference problem is a little different, and it's not as nearly as well worked out and understood as the problem that is typically done with inferential statistics. So there are times when you have all the population and there is no need for statistics. You may still want to know if this is likely to happen again in the future, but that's also a slightly different question. But anyway, in all of the stats we will learn in this course, we are doing an inference about an unseen population based on observations. So you can look at this population, and if we could see the population, we could see that, oh, it's mostly gold. There's maybe 2 to 1 in favor of gold over blue. But if I sampled 8 cases, this is not an unlikely uh, outcome that I get 4 yellows and 4 blues. And so now you might ask, is this, if you only see this, would you then conclude that this population is fair, is balanced and equal or fair? Maybe, maybe not. It sort of depends on how many you sample and what are the numbers you're seeing. But in general, any statistical test we will sample, and the mathematics behind it are the mathematics of determining whether the thing you observed could have happened if there were no difference in the population. So all of the most of the statistical tests we do are about asking that particular question. Is the thing we saw likely to have happened given some null hypothesis? And that hypothesis is often sort of a hypothesis of no difference. In this case, it might be that there are an equal number of blue and yellow, but it could be that there's 10% blue and 90% yellow. And so just keep that in mind. Whenever you're doing a statistical test, you're drawing an inference about the population based on a sample. And some people, it's often easy to confuse that your test is not about your experiment you ran, it's about the population. The test is not about how likely, how sort of reliable the numbers are in your experiment. It's about how likely they were to, how likely a pattern in the population is, or how likely that pattern could have been produced by a population where there was usually no difference. So always think, when you're trying to understand a statistical test, what are you drawing inferences about? What is the population you're sampling from? And that can often help understand what the right test is to do. Okay, so the standard scientific way of doing inferential tests is for hypothesis testing. And so we have different hypotheses or different cases, and we want to provide a balance of evidence for or against. And for many years, the most common way of doing this, and still the most common way of doing this, is called the null hypothesis statistical test, or NHST. And it's really well understood, but it is increasingly come under criticism. People misapply it. It doesn't ask the question people think it's asking, and there's a lot of reasons why it's misled people, and some people claim it's one of the reasons for the replication crisis in many scientific fields now, because of the way it sets you up to only find differences when they exist. People then approach the task of finding the difference. They don't recognize when there's a null difference if it actually supports the null hypothesis, and things like that. So the standard sort of, some call it a frequentist approach, or the null hypothesis statistical testing approach, works by assuming a null hypothesis and trying to find evidence against it. That is, you assume that you say, well, what's the null hypothesis of my population? And in this case, the null hypothesis might be that there's an equal number of yellow and blue balls. And then you ask, what is the likelihood that the thing I saw could have come from that null hypothesis? And in this case, because they're a balanced number, there would be a strong likelihood that it came from the case of the null hypothesis, and so you probably couldn't reject the null hypothesis in that case. That's the sort of standard approach where we work under this, we frame a null hypothesis, and then we try to find evidence that rejects that null. And along the way, what most standard statistical tests do is they assume that the sampling process arises from some probability distribution. And so the observed numbers you come up with, whether they're heights of people, times, money spent, or whatever, arise because of some particular distribution. And then based on mathematics of statistics, we can make inferences about the likely values based on those distributional assumptions. So we know, and often the distribution is sort of baseline distribution assumption that's used is that the data are normally distributed. So in this case, since we're just sampling, this is just representing the sampling process, suppose that these are, two different groups of people that you're sampling from. Maybe they're two different political affiliations, and they give different sets of answers, but not completely different. Sometimes a blue will be in favor of something, or a yellow will be opposed to something that the rest of the yellows are in favor of. All right, so the classic statistical tests use the null hypothesis scheme and also make an assumption about the distributions. So this is sometimes called parametric testing, and the whole test centers on trying to find the likelihood of a false alarm, the likelihood that what you observed could have come from a situation where there really was no difference, where the null hypothesis was true. That likelihood is called the p-value. And so if you do a statistical test and you're looking for the p-value, that's telling you the likelihood that it could have arisen just by chance, essentially. That what you observed didn't come from any alternative, but it came from just what you expect if there's no difference. Because even if there is no difference, your sampling process will introduce variation. So what it's saying is that if, say, the mean height of the yellows and the blues were identical, and you happen to sample in a lucky way, what's the chance that blues are representative of the whole set of blues and yellows are the representative of the whole set of yellows? So that's really the question you're asking. You're asking how whether whatever you observed from the sampling you did could have arisen just by chance, and if it couldn't have arisen just by chance, then you'll conclude, oh, there must be some real difference in the population. Okay, so the classical null hypothesis statistical tests include tests you may be familiar with, such as the t-test and the ANOVA, and they're parametric because they make assumptions about the distribution of the data. They'll at some point assume that the values are normally distributed. Now, if you have large data sets, that's okay because you're really making assumptions about the form of your means, the distribution of the means, and that's going to converge to a normal distribution. But especially if you have small amounts of data, these might be considerably distorted if you have if some of these assumptions go wrong. And so an alternative that has emerged is what is called the non-parametric test. And a non-parametric test tries to find ways of doing the testing that doesn't rely at all on the form of the distribution of the data. And these can be useful in a few cases. In general, if you have a good sense of what the distribution is and you can model that distribution directly, you'll have a much more powerful test than a non-parametric test will provide. So you sort of get more bang for your buck if you can show that that it will be that you know the distribution. But there's a lot of different non-parametric tests that, and they can be useful if you know that your data violate assumptions of normality and you have small numbers or relatively small numbers, or if you just don't know. And if you have relatively small numbers of observations, something that's like highly skewed could, for example, really inflate your estimate of standard deviation, and you might sort of not have a really great estimate of standard deviation to form a test. So non-parametric tests are, in general, also null hypothesis statistical tests. You're doing the same approach, but you're relaxing the assumption of that you know what the distribution is. And often they use very simple transforms like rank. So if you do any so like the test will produce exactly the same results if you do any monotonic transform of the data. So you could take the log of the data and it will produce the same results. So that is sort of generally what happens with non-parametric tests, that you don't really care if it's highly skewed, because if you did some transform to make it unskewed, it would produce the same results. So both of these cases, non-parametric and parametric tests, use the null hypothesis, a statistical test. Both of them produce a p-value at the end, which is the chance that the outcome could have come under if the null hypothesis was true. And if that value is small, usually we use a criterion of about 1 in 20 or 0.05, we declare that it's statistically significant. Now there's a third approach that has emerged recently and started to become a popular alternative, and this is the Bayesian approach. There's a lot of different ways to do Bayesian inferential statistics, and we will, in this class, will cover one that is fairly simple, fairly straightforward to handle, because some of the libraries are out there that make it easy to do. There are much more complex versions that allow for really arbitrarily complex models with hierarchies and multiple relationships, but we're not going to cover those in this chapter, certainly. So Bayes factor tests are based on Bayes' rule. This is just a very simple example of Bayes' rule, which is a optimal rule for combining probabilities. And what it says is, if you're interested in the probability of something given something else, then you need, so A given B, then you need the probability of B given A, so you reverse. This is called the likelihood, times the probability of A over the probability of B. So you need to know all of these things. The probability of B is sometimes called the base rate or priors, and probability of B given A is called the likelihood. The likelihood is just the density of the distribution function at the point of the data. And so you can think of B as data and A as a hypothesis, or A as even a parameter. And now you can say, well, what's the likelihood of my hypothesis given the data? And by doing the math, you can calculate this. So this is a little trickier to do. Oftentimes you can't do it with closed form formulas. which is why people up until maybe 10 or 15 years ago could only do Bayes tests in very specific ways. And maybe the late 90s and early 2000s, the technology and the computers got to a point where we could do um, much more simulation based inference and do sort of arbitrary combinations of these things. So in this in this class, we will use an approach called Bayes factor. The Bayes factor is embedded within a library in R called the Bayes factor library, and this is in many ways sort of akin to the sort of null hypothesis test because it gives a single criteria value that provides a balance of evidence for or against your hypothesis. And that balance of evidence can actually the balance of evidence can actually be in favor of your null hypothesis. And so you can, unlike the null hypothesis test where you can just sort of ask, well, what's the likelihood of the false alarm? What's the chance that this came from my null hypothesis? This actually can provide you strong evidence for the null hypothesis, not just against it. And so the Bayes factor test is not non-parametric. It relaxes a different sort of assumption, and it uses a different way of calculating what's going on. Okay, so let's start by thinking about these null hypothesis tests. And in these cases, we are often interested in knowing what's the likelihood of the thing I observed given that the null hypothesis is true. And we'll start out with very simple versions of this, just sort of single experiments drawn from single means. So here is some example code, and this is very similar to some simulations we've done previously, but maybe I want to do 10,000 experiments. And in each time, I'm going to calculate the mean and standard deviation of my experiment. And here I'm going to specify experiment size, and I'm going to specify it to be 15. So this is like, you know, in a certain experiment, you so I have this at the beginning of this file. In a given experiment, you collect 15 values, and here we're going to collect them from a random variable that has mean 0 and standard deviation 1. Then I'm going to calculate the mean of those 15 and the standard deviation of those 15. So it seems like if it seems like we've done this before, we have. This will take a few seconds here to go. Actually, I'm doing 100,000. So if we were to look at the distribution of all the values, all of these data, we only see 15 at a time. We'd expect them to have a mean of about 0 and standard deviation of about 1. But what happens when we calculate the means on those? We see that it's for 15 items, this distribution has, you know, standard deviation of maybe about less than a half, somewhere maybe about 0.3. You know, like that's my eyeball estimate of the standard deviation. We can calculate it here, so it's 0.25. So here, this is a standard deviation of 0.25. And we could also look at a hist of the standard deviations, which we which were 1, and these are actually centered on 1, but they also have a distribution around them going down to, you know, 0.5 sometimes and up to 1.5 sometimes. So the standard deviations have a standard deviation. But so what's interesting, and what you should always try to keep track of when we're doing the inferential tests, is the distribution of the data is going to be larger. If we go back to here, the distribution of the data has a larger distribution than the distribution of the means that I collected from the data. So now let's say I want to know whether, so this is the null hypothesis, right? This is what happens if I do this repeatedly. And I think here is the figure that appears in the book. So this is what happens if I do this experiment repeatedly. That's what you'd expect under if the null hypothesis were true. And so in a null hypothesis test, it doesn't matter what your hypothesis is. This is the hypothesis you're testing against. So let's say we think that we run an experiment with 15 cases, and we want to know if the mean is greater than 0. So I've observed 15 things, and I see what they are, and all I want to ask is the mean greater than 0? Well, what we could do is say, well, I know that, let's say the mean was 0.1. That's actually pretty likely to have happened. 15,000 cases roughly occurred around 0.1. And so I would not, if the mean I observed from 15 cases is 0.1, I would not be very convinced. But I can go below, like this point, half of the observations are below 0. At this point, 0 or below 0, way down here. So I can actually do a cumulative distribution function over here to see how this to get a better understanding for how much of the density goes between or to the left or right of any criteria. So if I want to come up with some ad hoc criteria to say, well, is this really different from 0? I could come up with any number here and say, well, maybe this is good, 0.5. If I'm at 0.5, how many times when the null is true is the null as big as 0.5 or greater? So if I used 0.5 as a criteria plus 0.5, how many times would I be mistaken? How many times would there be a false alarm if I use this as my decision criteria? And it's hard to add these up and compare it to this, so we can do it from the cumulative density. And you can see here it's 0.975 or something. I think it's 0.977. About 2.5% of the time, this represents about 2.5% of the density. So that's maybe not too bad. If I set my criteria way to the right, further to the right, then I've got almost no chance of having that thing observed by chance. But at the same time, there is a high likelihood that even if there is a difference, I won't detect it. There's all types of sizes of differences that I might care about that I won't detect if I use too large of a criteria. And so the null hypothesis test essentially finds a criteria here and uses that. And even if you don't know what this, we don't just say let's use 0.5. It's done on some principled basis, but you can always sort of adjust it and say, well, I want it to be more lax or less lax, and you can see that there's going to be consequences. The higher the criteria you choose, the larger, the less likely you're going to find a false alarm. The more likely you're going to find, you're going to miss real differences that are small. And so in terms of most scientific disciplines, this is looked at as an acceptable balance. We want to be conservative about accepting new ideas, and so we say we're going to only accept your new idea, which is different from the null, if it's highly unlikely to have happened according to the null hypothesis. In other cases, you may have different criteria. I think in terms of making a decision about like an A/B test for a website, um, you may there may be cases where you don't want to start a new campaign unless you can prove it's better than a campaign you have a lot invested in. But if you're just choosing between two ads and trying to see which one drives more traffic, and there's no cost, the only cost is the cost of getting fewer ads, then you might be able to use very low criteria. Maybe if it's zero point 0.1, that's enough evidence to say that you should use one instead of the other. So now we've done this in exercise before, but what would happen if we um, increase this to say 20? To just speed things up, I'm going to reduce this um, to 10,000, and I'll run the histogram. And I want to compute the standard deviation of the means. So if I increase it to 20, that standard deviation goes from about 0.25 to, in this case, 0.22. What about 30? 0.18, 50, 0.14. You can see that the standard deviation of the means is getting smaller as I increase this. So here, if I double it to 100, it goes from 0.14 to about 0.1. In the exercise when we did 15, so if we wanted to plot these out, you could plot all of these out, and it does form a very systematic relationship. And that relationship is actually that the standard deviation of my means scales with the square root of n of my observations. So I could look at this and say, so I know that my standard deviation is 1, and so it scales inversely with the square root of n. So this was 100. If I go 1 over square root of 100, I get 0.2. What was the previous one? 0.18 when I did 50, or 0.14 when I did 50. So if I were to do 50, you see it's 0.14. And so these are being estimated, but just through random sampling. But I have an exact solution here based on proofs that you can do that says what that relationship should be. So I can say that the standard deviation of my means that I'm calculating is going to have a very specific relationship to the standard deviation of my data, and it's going to depend on the standard deviation of my data, which in this case is 1, divided by the square root of n. So the more n I have, it'll go down, but not linearly. It'll go down in relation to the square root of n. That value is known as the standard error, and sort of it makes sense that we use that value. Sort of the standard error is, here's the formula for the standard error. The standard error is the standard deviation divided by the square root of n. For a null hypothesis test, it makes sense that we use this when we plot error bars, because we care about how accurate our estimate of the mean is. And this really tells us what is the standard deviation of our estimate of the mean. We don't use standard deviation, which is generally because that's the estimate of the data, and because we're caring about inference, we want to know how reliable or how accurate our estimate of the mean is. And so this is what we generally will plot on a bar chart, as the standard error, or as the error bars. Okay, we just basically did this exercise. Okay, so here's the basic steps that we have to undergo if we want to do a statistical test. First, I call it step 0 because it's pretty important. We've got to convince ourselves that the assumptions of the test are not violated. And, the assumptions of a test, like what we're going to generate, the t-test, is that, first of all, the data are all independent. And this is often is not true. Like if you have multiple observations from a single person, you have non-independence. And if you have data collected over a time frame on different days, like purchases made over several different days, you won't have independence because things might change over those times. And so this is something that we usually either ignore or try to deal with in other ways. So for example, if you have multiple measures per person, they're certainly not independent, but you might just take the average of those measures for that person, or the total measures for that person. And so you only have one measure per person to sort of to have that independence. Okay, then we want to compute our estimate of the mean of the data we see, and then estimate the variability of our estimate. This is the standard error, which is going to be also computing the standard deviation of our data and divided by the square root of n. And if we go back to this, let's see, if we go back to this simulation, what we've been really simulating is a distribution under the null hypothesis for 15 samples with standard deviation 0, or standard deviation 1 and mean 0. So this has a hypothetical distribution that is well understood. It's called the t-distribution. So the t-distribution is the null hypothesis for this test, and the t-distribution takes on, as it needs to know the number of observations that went into it, because that's going to affect the shape of this. So once we have that, we can then use the t-distribution to set a criteria, not arbitrarily like we did with 0.5, but based on the chance of making one or another type of mistake. And so this is what we can get the t-distribution by looking at the pt function. And here I'm going to plot the t-distribution for different values of what are called degrees of freedom. The degrees of freedom are related directly to the number of observations. So here we have 2, that would be for 3 observations. Here we have 5, that would be for 6 observations. Here 15, that would be for 16. Here we have 50, that would be for 51 observations. So we have this in our examples here. And in fact, I'm going to also plot the normal density just for comparison. So here's what a normal distribution looks like. And then we'll see what happens if I just have 2 observations. It's flatter and less peaked than the normal distribution. If I go up to 6 observations, 16, 50, and as I approach a large number, I could do 500, it becomes indistinguishable from the normal distribution as the number of observations increase. That's the t-distribution under the null hypothesis. So it changes shape actually very little, a little bit, and certainly when you're out in this range, a t-value of 2 goes from very likely to not very likely at all, as you it's not ever very likely, but maybe 10% out here, or maybe even if you're looking both sides, 15 or 20%, I don't know, to something that's 1% or less of the area. So instead of doing this, we can use, instead of that was the dt, the density of the t, we can use pt to look at the probability to the left of a, to the right or left of a certain value. And so here's the same thing with 2 degrees of freedom as we said, if I do 1 minus pt of 2, it gives me the area to the right. PT will give me the area to the left. And so there's about 9% of the data out here, or 9% of the density out here. If I increase this to 5, it cuts it in half to about 5%. If I increase it to 15, it goes to 3. If I increase it to 49, it goes to 2.5. And that's essentially what we get from the normal distribution too. So as we observe more and more, this is just the law of large numbers at work. As we have larger and larger experiments, our data are going to approximate a normal, our means are going to approximate a normal distribution more closely. But you can see that the shape doesn't change much, so most of the action really isn't in here, but it's in the boost I get from my t that I'm calculating, because the t is calculated by dividing. The t value is going to get more extreme because the t is calculated by dividing the mean by the standard error. Okay, so here's some data that we'll play with for the rest of the chapter. And if we just look at sort of, just for a moment, histograms of these, or violin plots, we can see that actually x1 was normally distributed with a mean of 0, but it actually doesn't look completely symmetric. This one is normally distributed with a mean of 0.2, but you can't really tell. Here's 200 points with a mean of 0.2, and maybe now we can tell. Here's 20 points with a mean of 0.5, so it's a little further away from 0. Here is something with a much smaller standard deviation, and here's something that is highly skewed. In each of these cases, we might want to know if we are sampling from this distribution and we have specific examples, what's the likelihood that that distribution has a mean 0, or what's the likelihood that what we observed could have come from a null hypothesis distribution that does have mean 0. So, okay, these are the building blocks then of the null hypothesis statistical test. And to run a statistical test, here's the basic steps that we just discussed. You know, we sort of convince ourselves that our assumptions were met. We compute the mean, we computed the variability, the standard error, and then we compute this t statistic. And the t statistic is going to be the mean divided by the standard error. Then we'll look that value up under the null hypothesis, which is the t distribution we just visualized here, under the appropriate t statistic, and find out how likely was that t value to have occurred in an experiment just like mine, but where a difference did not exist. So here's the steps for the value x1 we'll try, which really was generated with a mean that is different from 0. So I'll calculate the standard deviation, then I'll calculate the standard error by calculating the standard deviation divided by the square root of n, or the square root of the length. Then I'll calculate the t value. So let's look at the standard error, that's 0.19. The t value is 0.155. Now, this is a very small t value. You can never get a significant result unless you have a t value that's, you know, relatively close to 2, and maybe sometimes larger than 2 depending on your sample size. So we can already guess that we're not going to find a significant result, in that this result was actually very likely to have happened just by chance. we can, that's a sort of one-tailed test. We could do, let's see, and I'm doing this wrong. I have it the proper way of doing this in the book, but so this is the way of doing it by hand. You calculate the t and then you look up your p-value. So my p-value is 0.438. What that means is that this result, I have results this size or greater if the null hypothesis were true. So it's really not very unlikely to have happened if the null hypothesis were true. So I can't really make a strong case that in this case the data differ from my null hypothesis. Now this is a little tedious. It's not too bad, but it's a little tedious and you should understand what's going on. But the function t.test will do this for you and do a lot of other things. Report the mean and the t-values. So we looked at x1, we were just looking at x1, and you can see my t-value is exactly the same. My degrees of freedom is 19, which I specified here is 19, and my p-value is 0.4389, which is exactly what I got out of this. So you could do this all by hand, or if you want to just get one value for a bunch of things, you could do it programmatically. But this will give me all these values. Plus, it tells me confidence intervals and what my actual mean was. So this is simply what is called a one-sample t-test. The one-sample t-test, I give it a set of data, and it just tests whether the mean of that is different from 0. The null hypothesis here is that that the mean had a value of 0. And here I'm going to use a one-tailed test and say it's greater. Usually we have our hypothesis entails a direction. You know, if you want to know if some supplement increases your ability to lose weight, then it fails whether there's no change in weight or whether there's a gain in weight. And so you only really care about the loss. And so you can then generate a more powerful test. By default, the t-test will use a two-tailed, two-sided t-test. And so you can give the alternative a two-sided, and now it says, well, that's my p-value is 0.87, that's even worse than the 0.48 when I do a two-sided. So I can do this for all of these, and all of these different data, and you can look at them and compare them to this violin plot. You know, so x1a was just like x1, except it had 300 data points, and we can see here, or 200 data points. The degrees of freedom is always going to be n minus 1. Because we have so many, that standard deviation, which is about the same, gets divided by something that's 20 times as large, or 10 times as large. And so my t-value gets much larger because of that. And correspondingly, my p-value gets very small. It means that even though, if we look at this, even though there's a wide range of the data, my estimate of the mean is actually really good because I have a lot of observations, and I could be really quite confident that a distribution that looks like this couldn't have come from a true population where the mean was 0. You wouldn't have. It would be very unlikely to have gotten a value of 0.1 if given the distribution we saw, if the mean really were 0. In the case of x2, I can do the same thing. And now I have a much bigger difference. We can see the mean is 0.78, although I only have 20. So this one's highly significant as well, but not because I have a lot more observations. And in fact, the t-values for these two are very close. This one's 3.7 and this one's 3.5. So you can get a large t-value either from having a large difference or having a small difference with much more observations. We can see here that I'm not sure why the confidence interval is infinite. I think it has to do with it being a one-tailed test. So if we look at x3, this is one that has both a smaller standard deviation and a smaller difference. And again, because the standard deviation is much smaller, even though we only have 20 observations, we're able to detect a small difference. That mean is about 0.24. Oh, the mean is about the same, but instead of increasing the n, we reduce the standard deviation. So these three cases are sort of compared to x1. Here's one where we had the same difference, the same standard deviation, but a lot more observations. Here's one we had the same number of observations, but a larger difference. And here's one where we had the same number of observations, the same difference, but a smaller standard deviation. And each of these three produced a significant result of this test, in that the result was unlikely to have happened if the true mean were 0, or the null hypothesis. What about this last one that's highly skewed? Now you might think, well, this has this long tail and it's got so much to the right of the line that it's bound to be significant, but I'm not sure what's going to happen. In fact, that is what happened. This long tail sort of balances things out, but you can see that in fact the mean or the median of the distribution, the center, is less than 0. So you can't always trust this tail, and you can't always trust this test, because the test certainly assumes we've got a normal random variable, and we don't, and so it may mislead us. It's really being compared to a normal random variable with mean 0, and because it's not, you may not be able to trust this as much. All right, so that's the null hypothesis standard statistical test using a t-test, and that should be something that you can do in your sleep. Even if you prefer a different test, you should be able to do that. And this is the one sample test. In these cases, we're just testing values against the null hypothesis that the mean is 0, and we can change from one side to greater or less than to do very specific versions of that. Okay, so there's what happens if you want to do a non-parametric version of this? So let's look at these distributions again. And we've in several times used the binomial distribution. And a binomial distribution just is how many times you like it to look at if a die is fair. So we could maybe think about this rather than as having means and a difference from 0 as testing whether a die is fair. And if it's positive, it's heads, and if it's negative, it's tails. So a null hypothesis might be a fair die model. This sort of transforms this distributional assumption into a non-parametric test, because now we just have to say, well, are there more to the right or more positive than negative? And if it were a fair die, and I did 20 observations, you'd have to see a large proportion of them greater than 0 to be convinced that it was fair. And if you remember back to our simulations of the binomial, we need for something like 20 flips, we need a large bias in order to be convinced. So even though the t-test in these cases, this case was not significant, this was not, all these the rest of these four were, we could do a binomial test and now not worry about the shape of these distributions and just see if it was likely to have happened by chance. So this is sometimes called a sign test as well, a binomial test or a sign test. And there are packages that have the sign test, which is a little easier to use than the binomial test. But the binomial test it just calculates probability, and you have to give it the numbers. So you could do binom test, and let's say in this case I think I had 20, and well, let's look at x1. If I say x1 greater than 0, that'll give me the yeses and nos, and I could do the sum of that. So out of 20 cases, I have 9 greater than 0. So what's the binomial test of 9 out of 20? Well, here is the probability of success 9 out of 20 is 0.45. And it says, oh, that p-value is 0.82. This is not very strong evidence that it's any different than 20. So this is I can also specify the p-value, so I could choose fair or not fair. In this case, the sign test will do p is equal to 0.5. Here's for x0, which really had no difference, and now the p-value is equal to 1 because I think there was 15 out of 30 cases, so it's exactly in the middle. But I could do this for each of them, and certainly if you're going to do this a lot, you're probably going to want to download a package that has the sign test in it, because I don't have to do this summing and length. I can just give it the values and it will do the test for me automatically. So if I do, let's see, x1, we did that. If I do, now here's the one where I increase the number, and in the t-test this was significant, and now in the sign test this is also significant. And how about x2? And here, this is also significant at a p less than 0.05 level. And so the sign test is also significant for x2, where I had a much larger difference for just 20 items. And now for x3, where I have the same difference but a smaller standard deviation, again we see that's significant according to the sign test. And now for this tricky case, x4, and now in this non-parametric test, the p-value is 0. I found that there's 45 out of 100 trials were greater. In fact, it looks like, if we got this right, 45 out of 100 trials were greater than 0. So actually there was more weight less than 0 than greater than 0. So luckily, I guess, this was not significant, although in the t-test, if we look back at that, it was a significant result, but in the opposite direction. So this one says, oh, the mean is greater than 0.5. And this one says, well, the mean is less, it's equivalently less than 0.5. Fewer than half of the observations were above 0. Now, it's not significant, but it is in disagreement with the t-test. So which do you trust here? I don't know. It sort of depends on what you're trying to get out of this. That's okay. So that's the binomial test, and the binomial test is really only useful for a one sample non-parametric test. When you have one set of values and you want to see if it's different from zero. And in general, it's not going to be as powerful as a t-test, but in this case where we violated the assumptions of the t-test pretty strongly, it also didn't mislead us and kind of gave us this more fair assessment, because the t-test is going to be probably influenced by these outliers way out here, or this long tail. I don't know if it's an outlier, but it's a tail. Okay, so finally, the final piece for this screencast we'll talk about is the Bayes factor test. And I'm not going to go into detail about how the Bayes factor is calculated, but we'll try to do some examples and see what is produced, the same examples we'll look at. And so this is a table that was based on something from, I think, Jeffries and Cass and Raftery, about how to calculate the Bayes factor and how to interpret the Bayes factor. And so we have, you have this intuition that 0.05 is a good criteria in a statistical null hypothesis test. What are good criteria according to Bayes factor, and what is a Bayes factor? Okay, so Bayes factor will sometimes, depending on the software, report it in as a Bayes factor like 1 in 50, 1 in 250, sometimes in decimals, and sometimes even in like log base 10. And so you have to be careful about how to interpret these. But these are sort of reasonable assumptions about what criteria to choose, and you can see that they're sort of symmetric. A Bayes factor is a ratio of evidence in favor of one hypothesis versus the null hypothesis. And so if you have a very small value, that ends up being strong evidence for the null. If you have a very large value, that means strong evidence for the hypothesis. And sometimes these are easy to flip around just by giving the function your data in the opposite direction. But so either a very small value, a lot smaller than 1, or very large value greater than 1 are good news according to, well, good news. They are evidence for one or the other hypotheses according to the Bayes factor. Now you should note that there is this mid-region between 3 and 1/3 that is an area of ambivalence. So this is something you don't get out of a null hypothesis test. If you don't have enough data to sort of disambiguate the hypotheses, your Bayes factor will be in this area. It'll be close to 1. It won't be much larger than 1 or much smaller than 1. And here you just can't tell. Now, in general, in the null hypothesis test, whenever you are not significant, you're in this zone where you can't tell. And only if by doing secondary things like estimating power can you convince yourself that maybe there's evidence that the null hypothesis is true. So the whole notion of rejecting the null hypothesis, you're always saying, well, I can't reject it, and so I don't know the answer. But with the Bayes factor, you really can know. And so this is really nice for more both scientific decision making, because you can provide evidence for or against different hypotheses, but also for less scientific endeavors. If you're trying to make a decision for a customer about which design to use, you're not in this case where you say, well, I've got this great new design and it's marginally significant, or it's p is equal to some value. You can say, oh, this is, if we want to compare these two, we're really, it really is no different than the null, or it is really very different than the null, or we need to collect more data to make a decision. So it gives you three different paths. One is that I can confidently say that the original design is better, and one is that the new design is better, and one is that we don't have enough data to decide and we need more data. So it changes the whole dynamic of how you make decisions based on the statistical tests in many more practical applied settings. Okay, so we'll just finish off with one sample Bayes factor t-tests. The Bayes factor tests are in a library called Bayes factor. So I guess I'll add this here. It's capital Bayes factor. And, or no, what is it? I have not installed it. I'm going to have to install this. And there are, as this is, I think this probably takes a while, there are a number of Bayesian hypothesis testing approaches and dozens, if not hundreds, of libraries within R for doing Bayes analysis. And some of them are very complicated and permit a lot of flexibility, and others, Bayes factor is probably the simplest and gives very direct approaches for testing hypotheses and making decisions based on these criteria. And so it's useful for that. But there's others you can explore for other types of estimation problems and other types of inference problems. Okay, so the t-test, it's not really a t-test, but they call it a t-test because for compatibility with the t-test, it's called t-test BF for Bayes factor. So I can look at X, and it's a little difficult to interpret. It doesn't give you as much detail. But again, we have a single set of values, and it says the Bayes factor is 0.23. It gives me this R is 0.707, and this is a assumption being made about the priors. We talked about how you have to make an assumption about the priors, and here it's an assumption about what the possible values for alternative hypotheses are. What are the legitimate possible values in comparison to the null, and you have to make sort of some type of prior about that, assumptions about that. And this has been a value with a certain form that's found to be convenient and doesn't bias you very much in either direction. So here the Bayes factor result was 0.23, which would be actually fairly strong evidence for the null. If we go back to our table, 0.23 is in this range. It's positive evidence for the null. It's not strong, but it's positive. So you might call this positive evidence for the null hypothesis for x1. Now, x1 was really, remember, let's see, mean of x1 was 0.03. x1 was really generated to have a mean of 0.2, but it didn't turn out to have a mean of 0.2. It just by chance, we generated it from a random variable that had a mean of 0.2, but it didn't turn out that way. And so in this case, the Bayes factor actually makes an error in a sense, but the error is not really in the Bayes factor, it's in the data. We happen to get unlucky with our data, and the data turned out to be something that's fairly strong in favor of the null. To see this, we can actually you use a different, instead of the standard error, you usually will simulate from the model to get the possible values of these parameters. And so you can do that in the Bayes factor model by doing turning posterior to true and then saying how many iterations you want. And so here it's sampled from the posterior distribution that it had represented, and we can look at what these posterior distributions of mean and standard deviation are. This is what it's assumed, what the possible values that could have created it, and we can see that the possible values that it could create of it are pretty broad, from positive to negative. It still favors the null slightly, but really with the sample size we have, we don't really have a good estimate of what that mean is. It could have been values anywhere from about negative 0.25 to positive 0.25. Those are all reasonably likely to have produced the results we saw. And also considering that there's a wide range of standard deviations that would have been possible as well. Okay, well, we can do this for any of these results. So here is x0, which really was generated with something that had no results, and again we see a Bayes factor of about slightly less than 1/3, which is evidence in favor of the null. And that's, I guess, what we're hoping for there. Here is x2. If we go back, let's just go back to here. x2 has many observations, and now we see the Bayes factor. Again, this is always going to be 0.7 because that's an assumption that we could actually set, but it's very large. It's bigger than 3. If we look at our table, it's actually close to 20. It's almost strong support for the hypothesis. It's not quite there. So this would be reasonably strong support for the hypothesis. X3 was when we reduced the standard deviation and but had the same size mean, and now this is really strong support for the alternative hypothesis that there is a specific difference. And what about for this strange case x4? Now it shows again really strong evidence for the alternative, and it doesn't really say in this case whether it's greater than or less than 0, and we can address that using this is a two-sided test, and so I think we can do the null interval. We can specify the null interval. So maybe we want to say is this positive, and so I'm going to say the null interval is C of 0 to -2, and now it will give me evidence for the null interval and the I specified this wrong, -2 to 0. That would be the null hypothesis, I guess. And again, it's NA, so we've got this alternative here at 0.03 is sort of evidence against the alternative that it's positive, I guess. I could try specifying a null interval of 0 to 2, and we can see that now 0 to 2 has strong evidence in favor. So just like the normal random variable, this really considers this tail a lot more than this other side. Even though more examples are below, it this tail has a really large influence on the results, and we can see here strong evidence for a positive value, or really I think that's just the interval 0 to 2. So if I do interval 0 to 6 maybe, now it's so large, it's 32 versus 0.02 for the evidence for the alternative, which is less than 0. So in this case, rather than kind of having a null of no difference, we created two specific cases, alternatives, and we used the Bayes factor to find the evidence from the data for each of these. And one is very likely and one is very unlikely to have happened because of that. All right. So this is sort of the first step towards three different types of statistical tests using one sample tests. And that's the first part of chapter 8 up to through section 8.3. And in subsequent videos, I'll cover additional types, paired samples and independent samples t-tests, and then other sort of straightforward tests that also have both parametric and non-parametric and Bayesian versions, including the chi-squared test and correlation test for correlation. And then we'll discuss also things like effect sizes and how to calculate that, and some assumption checking. All right, well, so stay tuned for all of that. Thanks.